Kristin Knutson, production manager and technical director at the College Light Opera Company, coming to you from the stage at the Highfield Theater. Behind the Scenes with Kristin Knutson is made possible by a generous gift from Clyde Tyndale and Deb Winograd. This week, because we happen to have one on the stage, I want to talk about a piece of stage machinery commonly known as a turntable or a revolve. You've probably seen them on stage at your favorite musical, whether you realized it or not. There are many different ways to build a revolve and many different ways to motivate them or to drive them. I'm going to show you guys a mock-up, like a very small version of a turntable, just so you understand how they work. And I'll give you some clips and some information about different ways they can be operated. And we'll play around in the shop a little bit. So please come along with me and I'll show you how to build a tiny rudimentary turntable using scrap material. Stage machines are devices designed for the production of theatrical effects such as rapid scene changes, lighting, sound effects, and illusions of the supernatural or magical. Theatrical machinery has been in use since at least the 5th century BC, when the Greeks developed deus ex machina, by which an actor could be lowered to the stage. During the Hellenistic period, the Greeks also used movable scenery mounted on wheels or on revolving prisms called periaktoi. The Romans elaborated on these devices, adding traps and underground pumping systems so that their outdoor theaters could be flooded for aquatic shows. The mystery plays of the Middle Ages also used stage machinery, including a trapdoor or a hell mouth for the emergence of devils and flying machines for angels. The early Italian operas were famous for their special effects. Ocean waves were simulated on stage by painted spiral columns, laid across the stage in diminishing perspective, and slowly turned. Mock sea monsters and other fabulous creatures were operated by teams of men inside them. Deities mounted on clouds flew on complicated systems of wires, and portions of the theaters could even be flooded for water spectacles. Magical illusions were developed to a high art on the 19th century English stage, which produced great refinements in the use of trapdoors and mirror devices for the simulation of ghosts and apparitions. In general, the picture frame stage of the later 19th century allowed the refinement of extraordinarily vivid spectacles, realistic and otherwise, by the use of treadmills, moving panoramas on stage, and other stage machinery. In the early 20th century, particularly in Germany, much use was made of revolving turntables and hydraulically elevated stages, on which complex scenes could be preset and then brought into view when needed. The theatrical turntable, also referred to as a revolve, can be constructed and operated in a myriad of ways. They are most commonly constructed as a circular platform centered on a pivot point, sometimes surrounded by additional platform decking. They can be as simple as a single plywood disc, supported by a series of wheels and pushed by a stagehand, or as complex as concentric rings with independent computer automated control, variable speed, and possible incorporation into hydraulic stage lifts. There's really no shortage of options, thanks to the turntable's frequent use in industrial applications. I'm sure you've all seen an automotive turntable on a showroom floor, or perhaps turntables on a factory assembly line. The ideal turntable for a theatrical production is determined by many factors. How fast does it need to move? How much weight must it support? Will noise from the mechanism be a problem? Are there any integrated trapdoors or effects? Does it need to be portable for a touring production? How much time will stagehands have to load in and out? And of course, what's your budget? Let's build a miniature turntable mock-up with some scrap materials in the Highfield Scene Shop, and then I'll demonstrate some of the ways that a revolve can be powered. The size of my mock-up revolve was determined by a scrap of 3/4 plywood I found in the shop. Here I'm preparing to cut a 21-inch circle for the turntable's mini platform. There are several ways to cut a perfect circle. In my opinion, the neatest and safest method is with a router. The first thing I'm doing here is preparing a homemade circle jig, which will behave like a compass, allowing the router to swing around a central pivot at a specific radius. I need to clear some material on the arm to allow space for the router bit, both for function and for visibility. But of course I forgot a jigsaw, and I don't have the bandsaw blade with me at the moment, so here I'm using the table saw to nibble away at the wood. I temporarily removed 3 machine screws from the router's base plate so I could use very small wood screws to fasten the router to the circle jig. Once the 1/4 inch diameter straight cutting bit is inserted in the router, I can take an accurate measurement from the bit and mark my pivot point distance on the arm. I'm drilling a hole at my desired center point for the turntable. This will allow me to bolt the circle jig in place, and it will serve as the pivot or axle for the assembled revolve. After test fitting the bolt, I clear a little more material on one side of the plywood with a larger drill bit, which makes room to recess the head of the hex bolt. Now I can mount my circle jig to the pivot and set the depth of the router bit in preparation for my first cutting pass. I'm using a 1/4 inch straight cut plunge bit, also referred to as an end mill. Straight cut refers to the type of cutting edges or flutes. These run parallel with the length of the bit, unlike upcut and downcut bits, which are spiraled and drive the wood chips upward or downward, affecting finish quality. End mills do not include a guide bearing like flush trim and pattern or template bits. I'll be cutting the circle in multiple passes, largely out of caution because I don't want to break this bit. A good rule of thumb, don't cut much deeper in a single pass than the diameter of your bit. With a 1/4 inch router bit, I should aim for approximately 1/4 inch cutting passes as I gradually work through the depth of the material. Of course, it's possible to cut all the way through this material in one go, but then I would run the risk of stressing and snapping the tip. Before cutting all the way through, I blocked up the plywood with another layer of material to protect the table surface. A sacrificial layer like this is sometimes called a spoil board. And our plywood disc is free. I'm sanding it just a little to protect my fingers from splinters later. Here I'm preparing a base for my turntable using pieces of scrap material. I'm using lengths of pine to scab together smaller scrap pieces of plywood into a larger plate. This base will support the wheels and pivot for my turntable and make my mock-up unit easily portable. I'm quickly finding a center point on my base plate so I can scribe a circle as a guide for caster placement. I'll mark my center point with a screw. Now I'm determining where to put my casters. I'm only going to use 4 because this turntable is so small. If I were actually building this turntable full scale, I would use straight or rigid casters to support the platform disc. You want the orientation of the casters to be locked in perpendicular to imaginary lines radiating from your pivot point. However, for this mock-up, I'm using small, hard plastic swivel casters I picked up for cheap. The swivel would be problematic if I let it swing freely, so I'll be blocking the swivel forks in place as I install these casters. I prepped a strip of scrap pine with a rabbeted or grooved edge. I can cut this into small blocks that fit tightly over the thickness of the caster plates. The casters are secured wheels up on the base plate. First, I'm aligning and screwing down the caster plates, then I'm fine-tuning the wheel alignment as I block the casters to prevent swiveling. The frequency of caster placement will largely depend on the caster's load capacity and the rigidity of your platform disc. Turntables with no framing and only 1 or 2 layers of plywood will require casters every 2 to 3 feet in an array from the center point. Any less, and you'll notice squishy spots when you stand on the revolve. The hard plastic and loose fit of these wheels and their forks will generate more noise in comparison to rubber wheels with tighter tolerances and bearings. With wheel hardness, you are trading friction for noise. A harder wheel will get rolling easier, but the rumble will be much more noticeable. Now I need a way to capture the revolve's pivot point or axle. Gravity is your friend when it comes to turntables. Usually you don't need to worry about a revolve jumping off the ground, so all it takes is a receptacle for a pin. I'm using a hole in a block of wood and a bolt for this mock-up. Large scale, a sleeved pipe or short length of steel shaft would do the trick. As long as the receptacle is very secure, the turntable itself can simply drop right on top. So, what motivates a revolve to move? This mock-up is obviously manual and requires a human to push it. The most common types of powered turntables run by friction drive, cable drive, or direct drive. Friction drive requires a motor-driven wheel pressed against the outer perimeter of the revolve or a hidden inner ring, and sometimes uses an encoder wheel that tracks position for repeatable cues. Since the mechanism is usually external to the revolve, they are easy to service but tend to take up a lot of space and require a deeper deck height. As an extremely rudimentary example, pretend this drill is a motor-driven wheel. Cable drive uses a tensioned belt of cable or chain connected to a hand-cranked winch or motorized drum. When the winch rotates to draw up and let out cable, the turntable rotates with the motion of the belt, provided the tension is sufficient. Cable drive mechanisms can be hidden away pretty well. The cables can run under elevated decking to a distant corner where the winch motor is less likely to be seen or heard. Another very simple example. Imagine this line is a tensioned steel cable, and my hands are a rotating drum. Direct drive turntables typically have one or more motors hidden under the deck within a center ring. These motors are geared to a toothed ring for very precise movement. Direct drive turntables have fewer problems with slippage since they don't rely on friction alone and can be neatly self-contained thanks to internal motors. However, self-containment does mean access for maintenance is a little trickier, requiring trap hatches or partial disassembly should something go wrong with the motors hidden within. With my mock-up disc lifted off, now you can clearly see the path of the casters on the underside of the wood. And finally, just for fun, I decided to give my glorified Lazy Susan a spin. Not the smoothest, but it stands up to the weight test. Let's look at a full-sized turntable. At this moment on the Highfield stage, an approximately 18-foot manual turntable remains in place for a delayed Falmouth Theatre Guild production of Chitty Chitty Bang Bang. It is effectively a full-scale version of my mock-up, with layers of plywood forming a very large, unframed disc, and an array of rigid casters mounted to a substrate of plywood on the stage floor. An operator would sit or kneel at this spot upstage and grip the edge of the turntable to move it. You can't quite see it in the dim light of my camera flash, but the central pivot appears to be pipe with a pillow block mount for smooth movement. I can move it with one foot without much effort, even though the weight of the plywood disc alone is close to 500 pounds. I'm going to quickly attach a rope and take these old lighting instruments and chairs for a whirl. Please note that most of the rattling you hear comes from the lighting instruments bouncing. This is actually a very quiet revolve. As you watch from the underside, you may notice that not all of the wheels are rotating at the same time. This is due to very slight warping of the platform disc, causing a brief loss of contact with the wheel. With the turntable safely locked off again, it's time to say goodbye to the Highfield for today. Before I close off for this episode, I'd like to share some images from the recent concrete work on the new rehearsal hall. Thanks for joining me today. Behind the Scenes with Kristin Knutson is part of our larger series, Digital Clock. Digital Clock is made possible by a generous gift from Phil and Liz Gross. If you'd like to learn more about our programming or how you can become a supporter, please visit us at collegelightoperacompany.com. Join me again next week. I'm going to give you guys a brief history of theatrical lighting and give you a peek into the ongoing electrics maintenance happening here in the Highfield.